Hi guys, my name is Xuanshen Wu. I'm the second year PhD student in computer science at the University of Georgia. So today I'm going to present our paper titled with the matching exemplar as next sentence prediction, MeNSP, which is about zero-shot prompt learning for automatic scoring in science education. So this talk will include three sections. First, we will introduce some background about automated scoring for science education assessment, and we will discuss some limitation of the existing methods. Then we will introduce our proposed framework, MeNSP, which is basically based on the prompt learning techniques. And we will show that how to use the prompt learning to solve or overcome the limitation of traditional machine learning models. Then we finally conduct the experiments and focusing on answering the following three research questions, which are the how accurate is MeNSP in automatic scoring without training, and how does the MeNSP benefit from a few samples. Finally, we will discuss about how is MeNSP sensitive to the sample qualities. So let's talk about some background about automatic scoring at first. So automatic scoring aims to evaluate it's basically fundamental of the science education assessment. So science education assessment aims to evaluate the students' competences in utilizing scientific knowledge to solve the problems and design solutions. So in practice, the teachers begin by designing scientific questions and along with their the grading rubrics of along with these question items. So subsequently, the students are asked with a response to these questions, and finally, teachers will assess the student response based on the provided grading rubrics together. So typically, grading rubrics are described in the natural language, which can result in varying interpretation among different graders. So to achieve the fair and reliable grading result, educators must invest a significant time in formalizing themselves with the rubrics and grading the responses. So one way to scale up this process is adopting the traditional machine learning models. The main difference is that the educators could collect some graded responses and let the machine learning models to learn the mapping between the response and their grades. So once the model is obtained, it could be easily applied to a lot of the student responses grading situations. So one significant limitation of these traditional models is we need to collect a lot of the training data. And they should be very high qualities. So in practice, it's not easy to achieve that, which is a very time consuming and expensive. So now we want to introduce our proposed MeNSP framework. So let's talk about the prompt learning first. So in the field of the NLP, the prompt learning has been studied as a sufficient way to overcome the future problems. So to overcome the core idea of prompt learning is to align the downstream task to one of the pre-training tasks so that we could directly use the pre-trained model for our downstream task here. So one of the naive way to achieve this is to apply the pre-trained language model to our task. Our task is to reformat our scoring task as a mask language modeling task. Well, specifically, we could design a template that combines the rubrics and the responses together with the mask position. So we help the model to fill the score at the mask position. directly by using directly the pre-trained models. However, we found that these strategies fails in practice. Well, basically the model almost randomly fill the numbers here. So we believe the main reason leading to this phenomenon is that the task definition is not clear enough. So because we have a limited context window, so we cannot write down a lot of a very long description of the task definition. Um, Also, the other problem is that we believe there's a gap between the rubrics and the grading levels because the rubrics is a very high level natural language description, which just tell what's the perfect she looks like. And there's no any numbers or something like that. So there's a gap between the natural language rubrics and a specific the grading levels. So to solve these two problems, we proposed our MeNSP strategies. Basically, we first switch from the mask language model task to the next sentence prediction task as our auxiliary training task. So basically, instead of describing the definition of the scoring task, we want the NSP task to can because the MeNSP task it originally is focused on to estimate the probability of a pair of sentence that falls into the same context. So the secondly, we also want to, instead of the inputting a pair of the student response and the rubrics, we propose to match the student response with the exemplar response at the specific grading level. So we can literally combine this student response with each exemplar response at each grading level and assign the final score that the model believes that they match most. The whole framework can be formalized as this equation. So a more detailed design of this architecture can be presented in this diagram. So basically, we just concatenate the student response and the exemplar response at the grading level G together. And the pre-trained BERT already has a head classifier layer that can classify whether these two input tags or segment in spans are falls into the same situation, the same context or not. So this framework works well on the most of the situation, but it almost fails in all the zero score response grading. That is because it is impossible to exhaustive all zero score responses. The reason is that, well, one response should be graded as one score or two score, full score, should be have exactly the reason. But there are many of the reason can be make it as a zero score. So we cannot exhaust it, all the zero score responses. Then this model fails to detect those the zero score responses. To solve these problems, we propose to filter out those zero score responses at first prior to our main module. So that is means we directly give a zero score to a student response if its embedding is too far away from that of the perfect answer or perfect response embeddings. We use the cosine similarity here to measure the distance between the two embeddings. Then the threshold is set to the AIED similarity of the one of the zero score exemplar here, and the one score exemplar with the perfect answer embeddings. So by doing this, we can filter out those zero scored responses prior to giving them a specific score like 1, 2, 3, or 4. So let's talk about our experiments. In our experiments, we want to answer these three questions. More specifically, we want to know how accurate is MeNSP in scoring student responses. The second is, can the performance of the proposed model be further improved if a few sample responses are available? The third is, how does the quality of the sample responses affect the performance under the future setting? We conducted our experiments on items G4, G5, and G6 from the previous studies, and they totally have 2,081 records. We should note that we only keep the three samples at each grading levels at each item as the training set, and the rest of the data at each items are be considered as the testing set here. So it's totally a zero-shot setting. So under the zero-shot setting, the three samples will not be visible to the models. So we evaluate our model with the F1 score and the Cohen's kappa parameters. So we will test our model with the 5 random seed, and we report the mean and standard deviation of our results. So let's look at the first result here. So we first evaluate our model under zero-shot scenario where we do not train the model on our dataset. We can see that while the random guess strategy just gets around the 0.0 kappa performance, the proposed MeNSP achieves around the 30% the kappa scored on the G4 item and maximally achieves the 57.2% of the kappa score on the G5 item. So it shows that the MeNSP can effectively score responses based on the context and exemplars without training. Now we talk about the future performance. So the result of MeNSP here that is fine-tuned on 1 or 3 samples from the dataset. So on the item G4, we find that the MeNSP gradually improved its performance from the 30.3% to 35.9 kappa with the one sample, tuning on one samples, then further improved to 37.5 kappa coefficients with the 3 samples training. However, this trend doesn't hold on the G5 and G6. Well, since G5 and G6 are classified as harder questions than the G4 from the original dataset paper, we conclude that MeNSP can be improved by training on a few sample responses on the easier items. So we now analyze the MeNSP future performance by providing manually designed samples or randomly selected student responses. Generally, it shows that the manually designed samples are generally poorer than the random selected samples. It's probably because the manual designed samples falls in different styles to the student written response. Basically, it's what our orders wrote in the response doesn't look like the a student written responses. So it leading to out of distribution problems. It could be also considered as, but this phenomenon is also could be considered as evidence that we need to match Exemplar instead of the rubrics, because the rubrics coming from the instructor is much more diverse and different from the student response style. So basically, in our study, we showed that MeNSP could ultimately score the student responses based on the exemplars without the model training. And we also discussed the future training performance of MeNSP and find that it largely depends on the characteristics of the items and providing samples. So we hope our future works could explore our findings to more data set with with a recent proposed powerful language model like the ChatGPT or GPT-4. I believe you all know and familiar with them. Yeah, this is all the talk about this topic, and I'm ready for any suggestions, comments, or discussion here. Thank you very much.